First, we will recall the very important theorem that we introduced last time, the intercept theorem. Very important theorem. We have two triangles. One triangle and a line. A, B, C. The line intersect at E and F. The intercept theorem tells us that if these two lines are parallel, then this pair of sides will have the same ratio. Okay. Because this is an identity, now if we can use the proof by contraposition to show that this is actually equivalent. So conversely, if we have the same ratio, then the two lines EF and BC must be parallel. And the ratio of the third pair of sides is the same. Okay. So this is the very important theorem we have gone with several times. This motivates the definition for similar triangles. Yeah. If we can check two sets of conditions. First set about angles. Second set about sides.
That's a G.
Okay, yes, you're right. So this one should be G. Okay, thank you. Aaron, turn on the camera. And Jessica, Isabel, the cameras are off. What's going on? Okay. So the second set of conditions for sides. A, B, A, C. If these two sets of conditions hold, then we say the two triangles are similar. Okay. Now, using this new terminology, we can reformulate our results about the intercept theorem. It says that if these two lines are parallel, then these two triangles are similar. So reformulate. Okay. So okay. We reformulated the intercept theorem. And now we can see the structures of our theorems. So like the mathematics, we have is like a building. The fundamental one, we have the structure. The midpoint theorem, a very important theorem. Then we generalize the midpoint theorem. We have the intercept theorem. That means the intercept theorem is based on the midpoint theorem. It's a more general, it's for more general situations, and it's much more powerful. And based on this intercept theorem, we have quite a few similarity theorems. And in the future, we will learn more and more about the theorem. But you should have an idea how these theorems are connected. Which one comes first? Which one comes second? Becomes the third. So we used the midpoint theorem, the first big theorem. Then we get a much general version for the intercept theorem. Then we used the intercept theorem to get quite a few similarity results. Okay. So the similarity theorems. We first have the ASA theorem. ASA similarity theorem. Okay. We have a pair of triangles. For the congruence, we need the two angles. Let's see, angle A, angle B, angle F. This just AA, not ASA. Correct myself. Oh. For the congruence, we need another condition. The two sides between the connected two angles, AB equals EF. Under these three conditions, we have congruence. But for similarity theorem, we just need the angles. Okay. The second one is the one we had in our homework, SAS. It states that previously we said AB equals EF, AC equals EG, and angle A can be E. I can reformulate the first pair of conditions. Maybe it's a different color. Reformulate the two sides have the same length is equivalent to the ratio is 1. Fred, can you hear us, Fred? And Peter?
They can.
Okay, okay. So similarity theorem. Okay. You should see the difference and connections between the two theorems. For the SAS theorem about congruence, the ratio is 1. The ratio is, if the ratio is anything different from 1, then we have similarity. Okay. How do we move from congruence to similarity? And the last one, the one we had in our class, SSS. these two triangles are congruent. Again, we can reformulate. Then the corresponding theorem for similarity. Again, the ratio here may be different from 1. Okay. Now we have theorems about the congruence and theorems about similarity. The corresponding conditions from congruence to similarity, from congruence to similarity. And how do we go from congruence to similarity? The key step is the intercept theorem. How do we move from there to the intercept theorem? Okay, let me pause for a few seconds. Any questions? Aaron? Jessica, what about you? No question? Okay. So next, we move to a special class of triangles. A triangle with a right angle. Okay. So we will label this angle theta. Okay. And the two special cases. First one, 45 degrees. Not good. We draw this. Okay. Okay, let me check. Isabel, what can you say about the angle C?
45.
What's the degree of angle C? Okay, it's also 45 because the total interior angle is 45. Okay. Now, if this side is angle, side is 1, because the two angles are the same, this isosceles triangle, these two sides will have the same length. If we call this one x, this will also be x. Then by the Pythagorean theorem, the summation of the squares equals to the side, the square of the hypotenuse. From there, we have 2x squared, and x is positive, which is, okay, a second special triangle. Okay, Jessica, if one angle is a right angle, second angle is 60 degrees, what about the third angle?
It's 30 degrees.
30 degrees, nice. So we also want to compute the two sides of this right triangle. If this is the one, x, and y. This time they will be different, one longer, one shorter. To find the length, we will mark the midpoint. D. And last time we checked, ED equals CD equals AD. Okay. In particular, ACD. This is an equilateral triangle. Okay. Therefore, XAC, which is CD, is half of AB. Then we find the second side, y, is the Pythagorean theorem. We know that x squared plus y squared. And x is 1/2. Square is 1/4. Again, y is positive. In this way, we find the length of two of the sides of two special right triangles. One 45 degrees, one 60 degrees. Okay. And in this theorem, we have a very interesting observation. If we pick the midpoint, we connect the midpoint with the third vertex. This side is half of the length of the hypotenuse side. And this is true when the triangle is a right triangle. This is the theorem. we consider a right triangle. The side opposite to the right angle is the hypotenuse side. And the two legs. If we, again, we mark the midpoint. That conditions, again, we mark the midpoint. The conclusion is CD is half of AB. In general, this is not true. This line segment and this one, generally, they are very different, and not that dependent. For example, what happens if we have a triangle that's not a right triangle? For example, not right triangle. Now, if we connect to the midpoint,
That's the right triangle.
so
Oh, if you look at it from both sides, then
okay, A, B, C, D. Okay, maybe I should label this. Let me change my order of vertices. Let me change this to match our previous description. This will be A, B, C. So the point, so Aaron he observed this will be a right triangle, this is a right triangle. So if these two sides have the same length, then these two will be the right triangle. The point here is this angle is not a right angle, and CD is not half of AB. And in this particular case, CD is even longer than AD, not AB, not to mention this. If we're in a right triangle, we have this property. But in a general triangle, we don't have such a property. This median line may be longer than the total AB, not just half. In particular, if it's not a right triangle, then CD can be different from 1/2 AB. Okay, just a remark. Okay, so now we want to prove this. Why do we have this property? Okay, let's think about it. Where do we start?
the right triangle.
The right triangle. So this one, this angle is a right angle, the midpoint. How to check these two are related? We will use the first biggest theorem, the midpoint theorem. So D is a midpoint. Let's find another midpoint. Okay, now D is the midpoint of AB. E is the midpoint for BC. What does the midpoint theorem tell us? Okay, think about it. Okay, Aaron, yes.
That's if R equals 1/2.
Which is half of which?
Let's see, 1/2 of the points on the line,
Okay,
1/2 of
so
on the lines.
there are quite a few conclusions. So this is half of AB. This is half of BC. This is half of AC.
Ah,
Another one is that these two lines are parallel, right?
uh-huh.
Okay, so the midpoint theorem, DE parallel to AC. Okay, so this angle is 90. What about this angle? Isabel? Angle BED.
90 degrees.
Also 90 degrees. And how did you get this?
Because like DE is parallel to AC, and since ECA is like 90 degrees, so like I think it's called corresponding angles.
Yes,
So
yes,
it
because
like
yes,
so it
these two
means
are
like
the corresponding angles of two parallel lines. Very nice. Okay, similarly, let me check with Jessica. What about CED?
It's also 90 degrees.
Okay, Aaron answered it. So why?
Let's see. That E is at 1/2 of BC, and that BC is 180 degrees, so split into two, it's 90.
Okay, so there are two ways to argue this. One, because total is 180. This is 90, this is also 90.
Yep.
Second one, this again the two lines are parallel. Okay, maybe that's equivalent. Okay, that's one enough. Now let's check the two triangles. Triangle BD, triangle CED. I wanted to say they are congruent, but I want you to tell me why. What theorem do you apply to conclude that these two triangles are similar? We have ASA, SAS, and we have SSS. Which one do we apply? Isabel, which one would you apply? This one, this one. Why are they congruent?
because I think you need to prove that like CE is half of BC and like
Okay, the two sides, same length.
yeah.
Okay, we have a side condition.
And then I think you can also have to tell like DEC is like or like the same as DEB, yeah.
Okay, we have an angle condition. Side, angle, and what's next?
I think it's DC and DB.
Okay, another one, you can see this one is shear, it's a common side. Do we use this?
Yeah.
So the common side to have the side angle side theorem. Okay, so I will skip the steps, but I just tell you side, angle, side. All right. These two triangles are congruent. In particular, the corresponding side had the same length. This implies BD equal to CD. And BD is half of AB because D is the midpoint. So this completes the proof. Okay, so how did we prove it? Why? This is half of this. So we used the property that this is the right triangle. Without it, we don't have this property.
Why
Yes, Eric.
why is it called hypotenuse median theorem?
Okay, so because this side is a hypotenuse side, and this is the midpoint, we call this hypotenuse median, and it's a theorem about this hypotenuse median
I see.
area. Yeah, okay. And now we can go back. So from this condition, so given any right triangle, if we have this, then there must be a right triangle. To state that, we need to introduce necessary and sufficient condition. Necessary conditions and sufficient. For example, we have two statements. If P implies Q, if P is true, then Q must be true. In this case, we say P is a sufficient condition for Q. If P is true, Q must be true. Now, for Q to be true, P may be or maybe not true. We cannot go the other way. So Q
Wait, what about the converse?
Okay, so not about that. It's let me see. What's the connection between them? So this is not about the logic statement. This is about necessary and sufficient conditions.
Oh,
Okay, this is related. Let me finish this, and I will tell you the connection between them. Necessary condition of P. For P to be true. Q must. Okay, so these are kind of similar, but you see the subtle difference between them. Okay, different emphasis. This emphasis, if P is true, then Q is true. This one, if Q is not true, then P is not true. Okay, for example, P, but the two triangles are congruent. Very similar. Okay. And the Q, the corresponding angles, but we just pick one of them. Now we can see P implies Q. Here, that means this is a sufficient condition for this. And for two triangles to be similar, the corresponding angles must be the same. Q is necessary. Okay, so you see the connection between them. If P implies Q, an example, if two triangles are similar, then at least one pair of the corresponding angles have the same measure. So this is a sufficient condition for this, and this is a necessary condition for two triangles be similar. Now, if the other way also hold, if the converse is also true, so if P implies Q and Q implies P, this means the two statements are equivalent. Okay. This means P is a sufficient condition for Q. P is a necessary condition for Q. Sufficient, necessary. So P Okay, so it's about necessary and sufficient conditions. And we will have 5 minutes break. After the break, we have quite a few examples about necessary and sufficient conditions. Okay, 5 minutes break. Be back at 8:22. Okay, so a little bit abstract, but we will see more examples of this necessary and sufficient condition. So this, as the name suggests, it's a sufficient condition. If P is true, Q must be true. So P is sufficient for Q. If P is true, Q must be true. Q is a necessary condition for P. So necessary and sufficient. Let's recall the midpoint theorem. So it will be slightly different from the first time we learned it. Slightly different. You see the subtle difference. A, B, C. E. Okay, so that's our condition. Then with the line, if EF is parallel to BC, then F is also the midpoint of AC. The other way, we also proved that if F is the midpoint of AC, then EF is parallel to BC. The proof by contraposition. So now we can combine the two statements to one statement, the new midpoint theorem. Okay. This is a necessary and sufficient condition for this point to be the midpoint. And the generalization, the intercept theorem, we also reformulated this. Okay, we start with a triangle. A, B, C. We draw a line across the two sides. We showed that if EF is parallel to BC, then the ratios and we also showed the converse is true. Now we can combine them into one statement. The new intercept theorem. these two one-way implications become one two-way implications. This is a necessary and a sufficient condition for the ratios be the same. So that's our new intercept theorem. Let's consider a triangle, the Pythagorean theorem. If we have a right triangle, oops, too bad, let me redraw. A, B, C. Angle C is 90, implies AB. And now we can check, this is also, the other way is also true. If we have this summation condition, then it must be a right triangle. We can reformulate the Pythagorean theorem. So a lot of the theorems we covered before can be reformulated using our new terminology, necessary and sufficient. It goes both ways. And the last one, our is needed. Okay. Initially, we stated as this: if this is the right triangle, then the median, so the condition that's D is the midpoint. Of VP. So we use the midpoint theorem to prove this. And we can trace back the proof to get the other implication. Now we can reformulate the hypotenuse median theorem. Okay. So for these examples, it turns out one condition is necessary and sufficient for other one. But don't go over what is stated. For example, we cannot say these two are equivalent. This is a sufficient condition, but this is not necessary for this. And this is a necessary condition. Of course, it's not sufficient. So these are not equivalent. Isabel, questions?
No.
Okay, so with the difference of the statements, two one-way implications now becomes one two-way implications. They are equivalent. They are equivalent. And in the future, we will use this version of the intercept theorem. We use this version of the midpoint theorem. It's more elegant. Okay, so
Hey,
about
question.
yes,
Why are there so much theorems?
yeah. So why this so many theorem? Because unlike the previous one, the algebra course, we learn a lot of operations. So in geometry, we want to prove some more general facts, more abstract facts, but we have to build the facts, the theorems, one upon another. So this gave us more powerful tools to do something about the mathematics. Sometimes with two triangles, we can, okay, one example. I think you have seen this before. Okay, why do we have so many theorems? Suppose sometime there's a very tall tree. We don't know how to measure this. It's difficult to climb it, but if we can measure the angle, okay, let me see. To label this will be tall. And so this is one of our students. This is Aaron. We want to know the height of this tree, but it's too tall that we cannot difficult to climb up to the top to measure the height. What we do is we pick a sunny day, we let Aaron stand over there where his head projected to the same as the tip of the tree. Now, these two triangles are similar. If we know this distance and we know the height of Aaron, then we know the height of the tree. So this will be the height of tree equals A, B, E equals A, B over A. Okay, let me give one more step. The height of the tree over the height of Aaron equals AB over AE. From there, we can find the height of the tree. Oh, not that. Aaron, do you agree with this formula?
Where's AC?
Okay, it's AE.
Oh wait, yeah.
AE. Sorry. And why is this true?
Well, you're dividing the height of the tree by me, which means the distance from me to the tree is over the distance between me and that point.
Uh-huh. So this, because these two triangles are similar, the corresponding sides have the same ratio from similar triangles. Okay, that's one application. Okay. Now we go back to the right triangles. We will consider the case when one side has less 1, this angle is theta. Okay, so then the side facing theta, the side we call it sine theta. The side adjacent to theta, cosine theta. Okay. And we have checked 2 examples. Theta, cosine theta, sine. If this is 45 degrees, and in the very beginning we showed these 2 sides will have the same length, both equal.
Square root 2 over 2.
Yes. If this is 60 degrees,
Square root 3 over 2 and 1/2.
1/2. Now, if this 30 degrees, what happens?
They swap, I think.
Okay, yes, because if one angle is 30, the other will be 60. We swap the 2. If this is 0 degree,
then it's a it was a 0 and 1.
so we will consider a limit case. When this angle becomes smaller and smaller, you can see sine theta, it becomes smaller and smaller, eventually go to 0. So sine 0 is 0. But cosine 0, this side will have this approximate, the same side as the hypotenuse, which is 1.
That's what I said.
Okay, yes, I'm just explaining why.
I see.
Okay, so then 90 degrees we swap because the complement will be 90, so it will be 1 and 0. Okay. Then the Pythagorean theorem. This side square is the summation of these 2 squares. We get sine squared. So instead of write sine theta square, cosine theta square, this is 1. And we will use a short notation because we don't want to write parentheses every time. It's easier if we adopt the following convention. Sine square. Okay. So in the future, instead of write parentheses power, we put the power over there. Similarly, cosine power. In this way, we don't have to write the parentheses every time. Okay. So this defines, using the right triangle, we define the sine theta and the cosine theta for angles between how do we generate this? If an angle is bigger than 90 degrees, what happens? How do we define sine and cosine? This time, we assume this is 1. Oh, it's too bad. We do this. Oh, 8. Suppose 08 and last 1. Then this will be cosine. So here it's important, it's very important to know that this is not the length, but because it's going negative direction. So sine theta is positive in this case. It's the height, but the cosine theta will go this direction. It becomes negative. Okay. The connection between this, if okay, we can check the sine theta, but this is also sine 180 degree minus theta. So from there, we observe if our theta is bigger than 90 degree, less than 180. Similarly, cosine. For this angle, cosine be the length, which is the opposite number of this x coordinate. It's opposite cosine theta. Okay. So we can use this graph to find the sine and the cosine, or we can use these two formulas to find the sine and the cosine for angles between 90 and 180 degrees. Because the difference, yes, Aaron.
Are we gonna be calculating a function or something?
I'm sorry, what's that?
Are we gonna be calculating a function or something?
I mean, so given angle theta, we get a number. So eventually, we will have the trigonometric functions.
Check.
Okay, so that's what Aaron wants. Matrix. Okay, when theta changes, the angle, when angle changes, sine changes, cosine changes, this defines two functions. Previously, it's defined from 0 to 90 degrees. And through the previous formulas, we extended to further extend this function, we will use the unit circle. No, let me draw the circle first. This is a circle of radius 1. A circle of radius 1. It means for every point OA is 1. A has two coordinates, x and y. Then
Question?
yes,
Don't write that as HK.
which is HK?
The XY part.
Okay, if you prefer HK, that also works. Then I can change it to HK.
I'm just curious.
Okay, this is just whatever we call it, we use it. That's what's just for convenience. I can use HK. Then this will be H, this will be K. Okay, so the first property is that H squared, K squared. But the Pythagorean theorem is 1. If we measure this angle theta, then in this right triangle, we can see H is cosine theta. The K is sine theta. So we get the coordinate of this point A. H is cosine theta. K sine theta. Okay, you can see for any angle theta, the coordinate of the point on the unit circle in this direction is given by cosine theta and sine theta, the two trigonometric functions. Okay. And with some very interesting properties of these trigonometric functions. Let's consider a general triangle, not a necessarily right triangle. Make it more general. Not right. Okay, that's not a right triangle. A, B, C. Now I will draw a perpendicular line from A to BC. Oops, what's going on with this? From A to BC. Okay, if I call this angle beta, call this angle theta. Okay, let me ask you, how do you find this height using angle beta and AB? AD vs AB and angle beta. I claim AE is AB times sine beta. Why is this? AB could be much longer than 1. If AB is 1, then this will be sine beta. That's the definition. But when AB is different from 1, we can find length 1, then the two triangles are similar. Okay, we pick a point, E. Draw a perpendicular line. F. Then the two triangles. This implies EF equals sine theta. Sine beta. That's the definition. Triangle BEF similar BAD. So we have the two ratios AB over AD equals ABAD BE over EF. Okay, so from our construction, we know BE is 1. EF sine beta. So from here, we conclude AD. The cross multiplication will be AB sine beta. Okay. Now, we'll continue from here next time, but I want you to try to find a formula for AD using AC and theta. We used this part. I want you to try to use this part to give a new formula for AD. Okay, we'll stop here today. Any questions?